Hi, we're going to talk about survivorship curves, what they mean, how to interpret them, and how to make one, which is a way of looking at patterns of mortality and patterns of survivorship. This is in the Population Dynamics, Chapter 10 of the textbook Ecology, Concepts and Application. It's the 8th edition, and it's by Manuel, Molles and Sher. It was published by McGraw-Hill in 2019. I'm Sue Glenn, so let's get into the chapter here. Survivorship curves are a really nice way of summarizing the patterns of survival in a population, but survival is really the flip side of mortality. You use patterns of mortality to calculate survivorship. It's just nicer to talk about survivorship, and it's a little more optimistic, I guess. And there's a lot of different ways you can collect data to make a survivorship curve. So the three main ways of estimating survivorship is one using a cohort life table. Cohort life table means that you take all the individuals born at the same time and keep records of them from birth and seeing when they died and how they died. And this is really a lot of data to collect. You have to obviously live longer than your cohort, or you pass on your data to somebody else who can continue to follow the cohort and see not only when they're dying, you can also find out why they're dying. Usually we use more of a static life table approach where you have the death of the individuals where you've been able to identify their ages. So it might be you have the tree ages from counting the tree rings, or you could have counting the marks on the shells of turtles, or looking at, we'll be talking about a static life table using Dall's sheep, mountain sheep that have the horns will record their ages. So there's a lot of different ways of doing that. Some fish will record the ages on their scales, so you can estimate their age, but not everything is carrying around a birth certificate and letting you know how old it is when it's died. Very commonly, we'll use an age distribution. This is used in the U.S. Census. They're going to ask how old you are in the census, and they can see how many people there were of different age groups and get an idea as to when those age groups are dropping off, where mortality is occurring, so that you can look at the differences in proportion of individuals in each class to get an idea as to percentage of surviving to the next age group. So this assumes that those differences are from mortality and that people haven't just left the country or immigrated into the country and adjusted the mortality differences. So there's a great data set that Adolph Murray collected and put into a report in 1944 looking at Dall's sheep. And he worked at Mount Denali National Park, which is in Alaska. Huge, beautiful park. And he collected all the Dall sheep skulls that he could find over the years. And he basically made an assumption that the proportion of skulls in an age class was typical of how many individuals are dying of that age group. So if you have like 50% of the skulls are sheep that are 14 to 15 years old, then you know half your population died at the age of 14 to 15. That is the assumption. And it's not a bad assumption because he had 608 skulls. He had a huge collection. That might be a problem if you've only got 20 skulls, but he had a very large collection. In fact, there's a later data set with even more skulls in it. So he just continued to collect all of this data. One of the things that he found looking at the data was he constructed a survivorship curve, and we'll talk about how we're going to do that, but he discovered bimodal mortality. So modality, that's where something is, you get a lot of something at a mode. He had two modes in the data set for mortality. He had high mortality for the youngest sheep, so those were the ones under a year old, and juvenile mortality is very common for all species, as it is when we're at our most vulnerable. And then the second time is when the sheep are old. These sheep rarely live 14, 15 years, so he found that a lot of sheep were dying of old age, at the age of 9 to 13 years old, and the young ones in between, the ones that are 2 to 8 years old are doing fine. He didn't find very many skulls in those age groups. So they're able to get away from predators. They're not falling down the cliffs and killing themselves at the bottom. They are still able to be nimble and get away. This is the figure out of your textbook where they're showing you the data and how they plot a survivorship curve. And we're going to go over this in a little bit more detail. But really what you're dealing with the data set is you're looking at the different age groups. So we have the different ages in the first column of the data, and that is from aging or dating the age of death from those skulls. And then you can look at the number of individuals in each one of those categories. And then when you're looking at a survivorship curve, the x-axis has the age, and then the y-axis, instead of mortality, we're looking at the flip side of that, the number of survivors or the survivorship. And that y-axis, that dependent variable, is plotted on a log scale. So that's a log axis. So the little drop in the age from 0 to 1 is actually like 400 skulls, or 400 or 200 individuals, I think, were lost within that time period. But we can see from the shape of the curve, we can see that really most of the sheep live to a good old age, and then they seem to die quite quickly. We'll get to next slide. We're going to get to how we actually do these calculations. This is the data they used to construct that figure on the previous slide. So this is the life table for the Dalmatian sheep from the Murray report. So the first column is the age intervals. So we have skulls that were under the age of 1 and skulls going up to the ages of 14 to 15. The second column is how many skulls you had in each one of those age groups. So 121 skulls were from young sheep under the age of 1. And so we had very high mortality under the age of 1, and then you can see when they get up to the ages of 9, we've got huge mortality from that point forth. So a lot of the sheep at this point from 9 on are dying, and then you had high mortality of the young ones. The other thing to note, and I'm going to go over these numbers a little bit, is that you have to know how many total skulls you have, and that's this number surviving at the beginning of the age interval. So in this particular case, this is the data with 608 skulls. The age interval 0 to 1, all the sheep had been born. So all the sheep were surviving at that point. The next slide, we're going to go over how we do these calculations. So let me just go over how those calculations are done. So this is the previous table. We have ages on the first column. These are age groups. So we've got the starting with the sheep that are under the age of 1 and going to the sheep that are age 5 or 6, but this continued on. So we had additional ages further down. So all of these columns are going to go down to the bottom. If you started with 608 skulls and 121 of the skulls were under the age of 1, that's where these first two numbers come. So N is the number in that age group, or the number of the population that we're starting with, and then the D are the deaths, because those are the skulls. So if we take 608 skulls of sheep that were born and subtract 121, we're going to get 487 sheep left in the age group 1 to 2. Then 7 of those die, so we're left getting into the age group of 2 to 3, 480. Then 8 of those die, getting into the next age group is 472. So you can see as we're going down here, we're just taking the number of deaths, and those were skulls where the sheep were in that age group, and subtracting that from how many sheep you have left. So then we're going to be down here to 465. If we're looking for survivorship, survivorship is L, and this is calculated as a proportion. And so this would be how many you have. 608 were born out of the 608. So that's going to equal 1. This will be 487 divided by 608, and so on. So you get the proportion. This survivorship 1000, this is a crude value, and this is just to get rid of nasty little decimal points. So this value in the last column equals whatever is in the survivorship times 1000, and it's just to remove decimal points. Here we have the complete table. This is the slightly larger data set where he had actually 752 skulls. And we can see then we've simplified the first column so that instead of it being the ranges of ages, it's going to be the bottom number of this. So this is ages 0 to less than 1 and 1 to less than 2. So it was 0 years old, 1 year old, 2 year olds, 3 year olds, up to 15. Years old. And then the second column is how many individuals are surviving at this age. So all 752 were born. The deaths are 129 skulls that belong to sheep under a year old. So then you can calculate from the number of skulls, subtract that from the 752, we have 623 at the age of 1. And we go all the way down, we end up with 2 at the age of 15, and 2 die at the age of 15. So there are no 16-year-old skulls found. This is the proportion. So this is the survivorship, which is your number divided by your total. So 752 divided by 752. Down here, your survivorship is 7 divided by 752, 0.009 survivorship. And then the final column is just those numbers multiplied by 1,000. And you can see the advantage of that is to get rid of all these little pesky decimal points. So if we go back to this figure from the book, then the graph that they made is constructed using these numbers scaled to 1,000. And just make the graph a little bit bigger here. And so we have the age across the x-axis. We have the survivorship on the y-axis scaled to 1,000. And remember, this is a log. That's a log scale going on here. So we have very high juvenile mortality here. And then we have the wolves getting the sheep over the age of 9. As I said earlier, we are assuming that the number of skulls you find at a given time period is reflective of how many of that population are dying at that age, but that's assuming you haven't had new ones coming in that age group, and you've also assumed that you haven't had any emigration. You don't have like all the juveniles leaving like we know can happen with dispersal in some populations. So how would immigration and emigration affect the survivorship estimates that we're getting on these age distributions? Which is why a cohort analysis is much nicer, because you can see how many are coming and going. So we take these survivorship curves, and the shape of the curve, we can actually, like at a quick glance, get some idea of the type of mortality that's occurring in the population. So with those sheep, we can see a lot of the old ones were dying, as well as the juveniles. A type 1 survivorship curve is like we find in the dull sheep. That is where most of your mortality is the older individuals. The type 1 curve is what humans have. Most large vertebrates have a type 1 curve. So we invest a lot of energy into taking care of our young, and that way we have high survivorship until we get to an old age. Type 2 survivorship curves, it doesn't matter what age you are, you have an equal probability of survivorship. So it doesn't matter whether you are an old squirrel or a young squirrel. If that hawk gets you in its claws, you're a gone squirrel. So you have a constant rate of survival. It's common with songbirds. You see this in mud turtles. So you can find this in a number of sort of smaller vertebrates. And then a type 3 curve is where you have very high mortality in your young. And that could be like a plant producing tons and tons of seeds, but only a few of them get to germinate and become adults, or a sea turtle is producing lots and lots of eggs, but the little baby sea turtles get eaten before they get to maturity. But once you get in that ocean and get established, then you've got a good chance of living to an old age as a sea turtle. So a lot of fish are like that. They'll produce tons of eggs, and then a few will survive, get through that juvenile phase and survive to maturity. And even though these are laid out as separate types, obviously there's a gray area. There's differences between, or areas between these. It's not perfect. So when we're drawing a survivorship curve, we've got the x-axis, remember, is your age from 0 to whatever your max is for your species. Your y-axis is going to be survivorship. And remember, you're going to log that. You're going to go from low survivorship to high, whatever scale you're using. So a type 1 survivorship curve, you do have that little dip in losing some when they're juveniles, but then you do really well until you get to old age. So that's a type 1 survivorship curve. Type 2 survivorship curve, pretty constant survivorship throughout your life. And a type 3 survivorship curve, the young ones are in trouble, but then if they can get through that, they live to a ripe old age. So that's a type 3 survivorship curve. But you can imagine there would be things, you know, that fell somewhere in these middle regions as well. So that's a gross sort of oversimplification of the system. Oh, look, there's a much better picture. Let's take a look at that on the next slide. All right, so here we have a much prettier picture with some pictures of the animals. This is for the visual learner. So we have across the x-axis again, we have age. We have a log scale on the survivors on the y-axis. And remember, the survivors we just got from subtracting the mortalities. And you can see the type 1 curve has very high adult mortality rates. The type 2 curve is constant throughout your lifespan, and your type 3 survivorship curve is your mortality is in your juveniles. And it says here many invertebrates have a type 3. Many birds, small mammals, lizards, and turtles have a type 2, and many mammals have a type 1 survivorship curve. So we would expect humans to have a type 1 survivorship curve. This is looking at a plant that we're actually going to be talking more about. This is an annual plant called Phlox drummondii. You can see it's really pretty. It's a garden plant that you can grow. And they have different phases in their life. So remember, when you're looking at this, you do have to look at the whole lifespan, but it's an annual plant, so it's only around for a year. It has to set seed in the fall, and then those seeds lie dormant for the winter, and then they'll start to grow in the spring. So this is starting with the seed. So the age in weeks across the bottom is starting from 0 weeks to a whole year, which would be 52 weeks. And so as it produces tons and tons of seeds, and as the seeds are lying there in the soil over the winter time, they become less viable. So we have quite a bit of loss in those seeds. And then it'll start to grow. Once it starts to germinate, then it does pretty well. It doesn't have much mortality through growing and flowering. Maybe a little bit it's competing with other plants near it. And then it has sets its seed, and boom, then they all die. They die quickly. So it's just like the Dall sheep. You have infant mortality, so mortality of the very young ones, and then you have very high mortality right at the end of the year. So it's a very different kind of organism, but we see kind of a similar pattern. Here we're looking at, on the left, we've got a couple of birds that are doing a type 2 survivorship curve, or have a type 2 survivorship curve, where their survivorship at different ages is pretty well going down constantly. So the blue line is the white-crowned sparrow, and the red line is the American robin, and you can see that they just have a constant rate of mortality over their lifetime. The American robin is a little more visible because of its coloring. And then the common mud turtle, we can see once it gets past its very high rate of juvenile mortality, then it also has a straight line. So it has a constant rate of mortality throughout its lifetime. And look at the ages on here on this common mud turtle. You can see like they can live up to 35 years old. So once a mud turtle gets to be 3 years old, it's pretty, got a constant rate of survivorship for a long time after that. This is a desert shrub, and so there's a little picture of it in the background. It can produce 1,000,000 seeds, but the chances of your seed getting somewhere where you can have the moisture to grow and you're not going to get dried out and you're not going to get outcompeted are not so good. So out of 1,000,000 seeds, 39 plants on average survive to get to 1 year of age. So this is clearly a type 3 survivorship curve where your infant mortality is huge. And remember, when you're looking at this scale, this is a log scale up the y-axis. So if you're looking at a log scale, you've just got a huge number of little seeds and seedlings just dying, not making it, and then we can see that there's some competition going on for most of your life, and then once you get to a certain age, you kind of have it made until you die of old age. So type 1 survivorship curve, juvenile survivorship tends to be high once you get over that infant mortality phase, and then most mortality occurs among older individuals. In contrast, individuals with a type 2 survivorship curve die at equal rates regardless of their age, and individuals with type 3 survivorship die at high rates as juveniles and then at much lower rates later in life. So at a glance, you get quite a bit of information off of a survivorship curve. So if you look at the concept review questions at the end of section 10.3, you should be able to answer the first two. How would substantial immigration and emigration affect your estimates? And the second one, female cottonwood trees produce millions of seeds every year. Does this information give you a sound basis for predicting their survivorship pattern? And we will move on now, and we're going to talk about in the next presentation on age distributions. So see you there.